here we see the situation. Now we have this disk with a total moment of inertia that we estimate to be about 0.0011 kilogram meters squared. At the rim, and I didn't mention, but the distance to the rim is about 10.5 centimeters. At the rim, we have this net force being applied. That net force is essentially the 3 grams. Remember, all the other paper clips were there just to overcome the friction of the system. So we're saying that the net force is 3 grams times, of course, 9.8 meters per second squared, and that gives us 0.0294 newtons of force here. Now we're going to check out Newton's second law. We're going to see if Newton's second law really holds by doing some measurements in the system. We actually did this. The net torque is the net force times x. Remember, x is the distance from the center out to the point of rotation when the force is perpendicular. So that we have a net torque in this case of 0.0294 newtons times 10.5 centimeters, approximately 0.003, very close to 0.003 meter newtons. We multiply newtons by meters, essentially, converting this to meters, and we get meter newtons, not newton meters. We say meter newtons when we mean torque, and newton meters when we mean work. It's not absolutely essential that you do that, but it helps us keep things straight. Otherwise, we might talk about a torque and think we're talking about energy. And the meter newton of torque, although it has the same units as the joule, is not the same as the newton meter, which is a joule. Anyhow, we get a net torque of 0.003 meter newtons, moment of inertia 0.0011 kilogram meters squared. This implies an angular acceleration of 0.003 meter newtons, or 0.0011 kilogram meters squared, torque divided by moment of inertia, and that's 3 newtons per kilogram meter. Now, newtons a kilogram meter per second squared. The kilograms divide, the meters divide. Now somehow this gives us radians per second squared. The second squared, of course, goes through, but where's that radian come from? Well, when we divide a meter here by a meter here, this meter was part of the meter newton, part of the torque measurement, and actually contained a radian in it. Okay, this meter is just a meter of moment of inertia, and without going too far into it, the radian just kind of pops out here. It's a little bit subtle, but if you think about where this meter came from, where this meter came from, you see that we need to get radians here. Also, of course, we need to get radians to get an angular acceleration.